Limiting reactant problems are also fairly common ideas in stoichiometry, and I'm going to use here a relatively simple example that only involves limiting reactants between moles. That's usually all that we ever have in the Chem 51 class. Let's look at this equation. If I were to combust butane, which has the formula, remember, C4H10, and that combustion means I'm reacting it with oxygen. And if I did a complete combustion, I know I would make carbon dioxide and water, both these substances probably occurring as gases. In fact, everything in this reaction probably occurs as gases. Remember I pointed out to balance hydrocarbon combustion type reactions, usually the strategy that is followed is that we first balance the carbons, then the hydrogens, and lastly the oxygens, because any number I put in front of the O2 on the left-hand side won't affect the C's and the H's. So in this case, I might say, well, if I start to balance this with, I would say, well, with 4 carbons in butane would give me 4 CO2s, and 10 hydrogens would require 5 waters, because 5 times 2 H's in H2O is the 10 hydrogens. And then when I add up the oxygens, notice I have 8, that's 4 times 2, plus 5 is 13, so I'd have to write 13 over 2, because 13 over 2 times 2 would give me the 13 O atoms. We don't really like to see fractional stoichiometric coefficients, so the way to get rid of the fraction is to multiply the whole thing by 2 and write 2 C4H10 plus now 13 O2s make 8 CO2s and 10 H2Os. So that's my balanced chemical equation for the combustion of the complete combustion of butane. Now, maybe you have a question like this. If I burn 5 moles of butane with, let's say, 20 moles of oxygen, and I could ask the question, how many moles of carbon dioxide do I obtain in that reaction? What you're supposed to see about this is definitely a limiting reactant problem, because I've specified the amounts of both reactants, and that's always the way you realize that you're looking here at a limiting reactant problem. And so the way I would do this is start out with the given 5 moles of butane and ask how many moles of CO2 do I get. Now I'm assuming plenty of oxygen. And the ratio is 8 moles of carbon dioxide for every 2 moles of butane, and that gives me 10 moles of CO2. Notice it's a 2 sig fig number, since I wanted to say 5.0 moles here, and 20.0. I didn't want to get rid of those ambiguous zeros on the oxygen. Then I ask about the oxygen. If I start out with 20.0 moles of oxygen, and again the ratio here is 8 moles of CO2 for every 13 moles of O2, notice this comes out to 12.3 moles of CO2. In other words, the 5 moles of butane, assuming all the oxygen in the world, give me 10 moles of CO2, whereas the 20 moles of oxygen I gave you give you 12.3 moles of CO2. Always the limiting reactant is the one that makes the least amount of product. So in this case, the butane is limiting, and I only obtain 10 moles of CO2. On a test, always make sure to put a box around the CO2, make it very clear that that's the answer, because the point is you can't possibly make 12.3 moles of CO2 if you only have 10 moles of CO2 coming out of that butane.